This is Geometry Unit 4, Triangle Congruence by Tim Ryan, Ryan Gooden, me, and Timmy Smalls. So this is a Unit 4 overview. So you can click the one that you want to look at and slide. So 4.1 is classifying triangles. 4.2 is angle relationships in triangles. 4.3 is congruent triangles. 4.4 is side, angle, side. 4.5 is angle, side, angle, angle, side, and HL. And then 4.6 is CPCTC. 4.7 is isosceles and equilateral triangles. This is Unit 4.1, classifying triangles. So a triangle is a figure formed by three segments joining three non-collinear points. A triangle can be classified by its sides and its angles. So classification of triangle by sides. So equilateral triangle has three congruent sides. An isosceles triangle has two congruent sides. And a scalene triangle has no congruent sides, meaning none of it's equal and all different sides. And when classifying triangles by their sides, you should also note the lengths of the sides determine the type of triangle. For example, in a triangle, if there are two sides of 4 and 1, that was 5, this would be an isosceles triangle. I can show you examples right here. I can just show it before. So 4 right here and 4 right here, 5. This would be an isosceles. I can show you scalene triangle. Scalene triangle can be determined like this. This would be scalene, because no congruent sides. An equilateral triangle is all congruent, obviously. So this would be equilateral. Alright. 4.1 classifying triangles continued. So the classification of triangles by angles. Equiangular triangle. Three congruent angles. All three angles must be 60 degrees, no less, no longer. Acute triangle. So this acute triangle. This has three acute angles. All three angles must be less than 90 degrees. And a right triangle needs one right angle. The angle must be exactly 90 degrees. An obtuse triangle is an obtuse angle with one angle greater than 90. An example is in triangle, one angle is 130 degrees, the other two angles are 25, would be an obtuse triangle. Like this right here, this is the example, 130, 25, 25. This would be obtuse. And I can show you guys how a right triangle will look. A right triangle will look like this. So this is always like 90. This is always 90 degrees. So this is the right triangle. Equiangular triangle has all three congruent angles. So yeah, 60, like 60 right here, 60 here, and 60 there. 4.2 angle relationships in triangles. Angle side relationship. The largest side of a triangle is opposite its largest angle. The shortest side is opposite its smallest angle. So in interior and exterior angles, an interior angle is formed by two sides of a triangle, while an exterior angle is formed by one side and an extension of an adjacent side. The measure of an exterior angle is equal to the sum of the measures of its remote interior angles. In angle relationships, the complementary angles must add up to 90 degrees, while supplementary angles must add up to 180. So these are so far related to angle relationships. And isosceles triangles. Isosceles triangles, two equal side lengths must have opposite angles that also are equal. So in triangle angle sum theorem, the sum of the interior angles of a triangle is always 180 degrees, no less. And 4.2 angle relationships in triangles continue. So an example would be like if in the triangle angle sum theorem, the triangle has angles of 50, 60, and x degrees, then it would be x equals 180 degrees minus 50 minus 60 equals 70. So this is how you solve an angle sum theorem. And for exterior angle theorem, if an exterior angle of a triangle is 120 degrees, and one of the non-adjacent interior angles is 40, and the other non-adjacent interior angles would be 60, because 180 minus 120 would be 60. So I'm going to be explaining angle relationships in triangles. I'm going to be showing you guys some examples. So right here, this would be called interior angles because the angles are inside the triangle. So A, B, C. And for exterior angles, they will always be outside, like C, like E, D, C. Right here. And for complementary and supplementary angles, complementary angles must add up to 90 degrees right here, and supplementary must add up to 180. So it'll look just like this. And for my isosceles triangle, the two equal side lengths must have opposite angles that are also equal. So the sides must be equal and the angles also must be equal right here. And then for these are this is an example. So this is an example from the problem. Let me just look at it real quick. In the triangle angle sum theorem, if a triangle has 50 degrees, 60, and x degrees, always you must do 180 degrees minus 50 minus 60 and solve for x, which is 70 degrees. Because in a triangle angle sum, it must be 180 degrees. So angle ABC must always add 180 right here. And then for exterior angles, the exterior angles are right here. This is an example of exterior. The exterior angle is equal to the sum of the two opposite interior angles. So this would be two opposite interior angles, and this would be an exterior angle. And for this, the sum of the exterior angles of a triangle and any polygon is 360 degrees. I'm also going to talk about a vertical angle theorem. So the vertical angle theorem states that when two lines intersect, they have opposite or vertical angles formed that are congruent, meaning they have the same measure. This theorem helps in solving for unknown angles when given the measure of one angle in an intersection. For example, if there was an angle here, like angle 50, and here would be x, then it will be easy to know because these are vertical angles. So this would be x would be 50. X would be 50 degrees right here. And then this is my example. So this states the vertical angle theorem states that in a pair of intersecting lines, the vertical opposite angles are congruent. So since A and B are the two line segments that intersect at point O right here, then angle AOE would be equivalent to angle BOF. And then AOF would be congruent to BOE.
4.3 congruent triangles. Corresponding angles and corresponding sides are in the same position in triangles. Two triangles are only congruent if their sides and angles are congruent. An example would be in triangles A, B, C, D, E, F, G. example of this would be with the triangle ABC, which is congruent to JKL. For angles, angle A will be congruent to angle J. Angle B will be congruent to angle K. And angle C will be congruent to angle M. For sides, line AB will be congruent to JK. Line BC will be equivalent to KL. And lines CA will be equivalent to JL. Side, side, side. Side is one of only 5 triangle congruency reasons. It occurs when 2 triangles have 3 congruent sides. This is displayed in the ABC is congruent to XYZ. An example problem for this would be AB equals 12x plus 4. And YX equals 40. As both sides are congruent to each other, that also means they are equal. So you set each side to equal each other. While you do this, you do algebraic steps. This applies to both of the other sides. SAS, or side angle side, occurs when 2 congruent sides have an angle in between the side of the triangle. This is displayed in both ABC and QPR. During this, angle B is congruent to angle Q. QR is congruent to BC. And AB is congruent to PQ. ASA, angle side angle, is when 2 congruent angles have a congruent side in between. This, comparatively to SAS, has 2 angles on both sides of a side. AAS, angle side, occurs when there are 2 corresponding angles while having a non-included side. This is displayed as DEF, angle side. An example of an included side would be ASA. HL, hypotenuse leg, occurs when one leg of a right triangle is congruent to the hypotenuse. This is shown in the ABC and DEF. If you have one leg of a right triangle with equivalent hypotenuses, that is the reason.
Yeah. All right, so for 4.6, it is CPCTC, which stands for congruent parts of congruent triangles are congruent. And this means that if you have proven that two triangles are congruent using the previously mentioned methods by Ryan of SSS, SAS, ASA, AAS, or HL, then the unmentioned parts of the triangle that you didn't say in the proof are also congruent. So I'll draw an example of this up here. So let's say we have a triangle like this. And then we also have another congruent triangle, not drawn to scale obviously, that is connected to it. So using side angle side, we could say, let's just say these are equal, and then vertical angles, yada yada yada. We have SAS, these two triangles are congruent. However, there's still this side and this side. Let's get these letters. This side and this side, even though they weren't mentioned in the proof by name, through CPCTC, they are congruent. So because we've already proved that the triangles are congruent through SAS, AB is congruent to DE. That is pretty much how CPCTC works when you're using it in a proof. And it works for other proofs as well, like SSS, which I've mentioned here. And this just means that triangles, even if parts of them aren't mentioned, they're also congruent because of CPCTC. So, like I said, this is used in proofs when you are trying to prove that something is parallel, maybe, which is different from what I mentioned before. Or when you're trying to prove that certain sides of those triangles are congruent, which I did mention before. Or what I didn't mention was certain angles. So in this diagram here, we could see that these sides are congruent, and because of vertical angle theorem, these are congruent. Angle ACB and angle DCE. However, unlike I mentioned last time, angle B and angle A are also congruent to angle D and angle E because of CPCTC. Now, overall, what CPCTC is for in a proof if you're asked to figure out if a part of a triangle is congruent versus the whole of two triangles. For example, if we have this, we prove this, yada, yada, yada. Prove that these are congruent. In a proof, you may be asked to prove that angle B is congruent to angle E. And through CPCTC, that is possible because it's pretty much in the name. The congruent parts of congruent triangles, like these, are also congruent. So what this means is that because these triangles have been proven to be congruent, so is every single one of their parts, like angle B and angle E.
So, the next slide is on isosceles and equilateral triangles. And isosceles, as previously mentioned, is when two sides are congruent in a triangle. So let me just go right over here. So it just means when a triangle and then two sides are congruent. And because these two sides are congruent, the opposite angles are also congruent. So I mean, these and these are congruent. So you can also use this fact, the angles and sides are congruent, in a proof. And you could use that in a proof because if it says that it's isosceles and like as like a given, then two sides will be automatically equal, which then you could, I don't know, use to get angles or something like that. And then the next one is on isosceles and equilateral triangles. And equilateral triangles, again, means that all the lengths of a triangle are equal. So, so that's just, this is it shows equilateral triangle and all lengths are congruent to each other. So this is congruent, and that is congruent. And then if a triangle is equilateral, then by definition it's equally angular, like how these are equal. And this, similar to isosceles triangle, you can use this fact that all the sides and angles are congruent in a proof by, if it says that it's equilateral, then that means that, you know, that all the sides are congruent and all the angles are congruent. You could also, that would also mean that all the angles equal at least 60 degrees, because they ought to be equal and equal 180. So then you can also use that to get 180 degrees, or get all the angles,